So welcome back. So do you hear me and see the screen with outline?
Yep.
So anybody? Yeah. Very good. Thank you. Yes. So we say that we will continue with abstract data types, which is the second item in the outline of the whole course. So abstract data types, we start with the definition of an abstract data type, and then we instantiate it to sets, queues, and stacks. So let's start with the definition now. So what's an abstract data type? Well, informally, it describes a data store, where by a data store, I mean some data structure that stores values in different forms and shapes. For instance, a set, a queue, or a stack. All these are data stores. Sets, stacks, queues, etc. And they will have different definitions from the point of view of an abstract data type. So in general, the definition of an abstract data type contains 4 objects: the set of states, which can be infinite, the initial state, set of methods or method names, and a set of rules. So the intuition is that the state describes the content of the store. For instance, if you have a set of integers, then the state will be just a set of integers. And if you have a stack of integers, then the content or a state will be a list of integers, etc. The methods, they tell you how to manipulate the states or the operations that manipulate the states. So these are names of the operations that manipulate the states. And the rules tell you indeed how these methods work. So in which manner they change the states of the system and how they interact with the user. So if you are used to formal methods, then, or to math or logic, then usually you write such a definition as a tuple. If you are not used to this notation, it's fine. Just know that you have 4 components in the definition of an abstract data type: the set of states, the initial state, the set of method names, and the set of rules. So now we will go through these one by one, and we will, to make it easier, we will instantiate the definition immediately with that of a set. So S is a set of states, S init, which is a member of S. So one of the states is an initial state, M is a set of method names, and R is a set of rules. So let's see how this looks like concretely. So we start with sets. So this is just the definition repeated: set of states, initial state, methods, and rules. So now we look at sets. And we define these or describe these 4 objects one by one, how they look like for sets. And in particular, in this course, we will work with sets of natural numbers or sets of integers, but the framework can be instantiated to any kind of set over any data domain. And so it will be exactly the same, but just to make things concrete, we choose one data domain, namely integers or natural numbers, and we consider sets of integers or natural numbers. So the states, a state S is as follows for sets. So S is a set of states. Now, for the case of a set, this is just a set of integers. So a state in the abstract data type, which is a set, is a set of integers. In this case, 2 and 5, but it can be any set of integers. Now we define the initial state, as you see here. So the initial state is one of the states, a particular state, which you call the initial state, which for this abstract data type, we take to be the empty. So initially, the set is empty. Again, set of states. Each state is a set of integers. Initial state is one particular state, namely the one in which the set is empty. The third one is the set of method names, M. Here, set of method names. And in this particular abstract data type, we have 3 method names, operations, if you wish, namely the add, in which you try to add a new element to the set. And I emphasize the word try, as we will see later why this will be the case. We have remove, when you try to remove an element from the set, and contain, which as a query, which asks whether a certain element is currently inside the set or not. So this is a membership query. So this, now the rules tells you how the methods change the state. So R is a set of rules. So now let's look at a rule. So this is the typical form of a rule. You have 2 states, S and S prime, which we call the source and the target states. We have an operation, which is the application of a method. And then this can be performed only if some guard is satisfied. So again, what a rule tells me is that from certain states, I can go to other states by performing some operations, provided that a guard on the set or on the current state is satisfied. So an operation then applies a method to the current state, obtaining a new state S prime if the guard, which is a condition on the state S and S prime, if this guard is satisfied. So let's, and now in fact this we call a guarded command. Why? Because such a rule consists of 2 parts, the source state, target state, operation. And this is the first part of the rule, which is called the command. In fact, this is a name which is used quite a lot in program analysis, correctness analysis. For instance, if you have taken the course on programming theory, you know what a guarded command is, but you don't need to know. It's just that you have a command part, and the command part of such a rule is just that you start from S, you perform an operation, and you go to S prime. And then you have a guard. It is a guard. It means that the command can be executed only if the guard is satisfied. And these 2 parts, they define a rule. And one important aspect of this is that each operation corresponds to an atomic execution of a method. And this word atomic is very important, as we will see later. In fact, I emphasize the word atomic. So again, each operation corresponds to atomically executing a method, and in the process, changing the state of the system. So let's take a look at the rules that are defined for the abstract data type set. So this is the set of rules. Each rule is a guarded command. Now, this is an example of a rule, one of the rules. It's the add true rule. It means that if you are in some state S, then you can add X for some X to the set. So you obtain a new set in which you have added X. And if this operation can be performed if X is not already a member of the set. And as a result, you return the value true, which means that you have successfully performed the addition. So if you compare this with the general definition of a rule, you have the 2 parts. You have the command and you have the guard. So the command tells you that you change state from S to S union X, that you add X to the set. And this is done through an application of a method, add applied to 2 parameters, X and true. As a result, I obtain S union the set X. And the guard tells you this you can do if X is not already in the set S. So in fact, again, comparing with the general form, this is the source state. This is the target state, S union the singleton X. So the whole of this is the target state. And if you look at the command, now you see that you change states and you perform an operation. And if you look more closely at an operation, it consists of 3 parts. It's a method name, it's an input, and it's an output. So this will be the general form. Maybe one of the input or the output may be missing, but in general, an operation is that you take a method, which you identify by its name, which is add in this case. This is one of the methods for the set. You have some input value that you give. You get some output, say from the abstract data type or from the program later, which tells you, for instance, whether the operation has been successful or not. In the process, you change the state according to the rule. In this case, the rule tells me that I should change the state by adding X or taking the union with a singleton X. And this operation is performed atomically. So this means that it's one operation, you do the add, and if it's successful, you add to the set and you return the result. So this is one of the rules. We have 6 rules in the set. This is the second one. So the first one tells you that you can add an element X successfully to a set, returning the result true if X is not in S. The second rule is similar. It tells you that an addition or adding a new element will fail if X is already in S. So if the guard tells me that X is in S, then I can perform the operation, but I return the value false, and I don't change the state. So in principle, intuitively, this means that the addition has failed. But this rule is enabled if X is in S, just that it tells you that it's false and it does not change the state S. So again, if you are doing an add operation, depending on the guard, either you get back true or false from the abstract data type, and the abstract data type changes state accordingly. So if it told you that the operation was successful because X was not in the set, then it will also add X to the set, and otherwise it will not do that. Sorry. So any questions up to now, please? Okay, the next 2 rules, they concern the remove operation, in which you try. So you see that I told you that we try to add an element, for instance, in add, which means that it can be true or false. And the same thing here, we try to remove an element from the set. Now, if X is inside the set, if the guard is satisfied, X is inside S, then the abstract data type will return the value true to you, and it will remove X from the set. So now X will not be part of the set anymore. While the dual rule for failure is that if X is not in the set, if you try to remove it, then the abstract data type performs this atomic operation in which it accepts X, but it returns false, and internally it will not change its own state. And finally, we have the contain rules. So one case is that when X is inside the set, if you try to check for containment, then this operation contain, again, you apply a method to some input and output, X and true, and the state of the set is not changed, but if X is inside the set, then you get true. While if it's not inside S, then you get false from the abstract data type. In fact, this is the full definition of the set abstract data type. It's a set of states, infinitely many states. Why? Because there are infinitely many sets of integers. You have a finite set of method names. You have a single initial state, which is empty. The method names allow you to define the set of rules, each of which is a guarded command. The command has a source state, a target state. It describes to you how the abstract data type changes its own state. It has an operation which corresponds to the atomic execution of a method given an input and output parameters And all this can be done provided that the guard is satisfied. So any questions? I don't see any. If I don't see any and you still have a question, you can, yes, there is a question there. Very good. Chat. Do guards only use the source? In general, they can use the target state also. But in the examples that we see, we will consider in this course, they only use the source state. Good question. But in general, there is nothing preventing you from defining the guards so that they also consider the target state. Yeah, I mean, there are some, for instance, there are some abstract data types where you generate an arbitrary new value, which is larger than some input value. And you say that I can apply the rule if the source state contains something which is larger than the target state contains something which is larger than the source state. But this is more complicated than what we will consider in this course. In fact, we did some work where you had stores with elements that were integers, that were infinite, but you had some kind of logical clocks. So in such systems, you would like to generate fresh values. So in this case, you say, I can perform this operation, but I expect the new values or the new value of the logical clock to be larger than the previous one, the old one. Yes. Thank you. Good question. Yes, but this is beyond this course. But in principle, conceptually, yes. Okay, very good. So now we have defined this set abstract data type. Now let's see what we can do with it. So at the moment, it's just syntax. So again, if you know formal methods, what you do is that you have, this is what we call a formal model. And based on this, you define some operational semantics. So if you have taken the course on semantics, you know what an operational semantics is. You have this transition system where you have a set of configurations, possibly infinitely many, and then you have a transition relation on them. So all of this, I will abstract away, just describe it on a very intuitive level. Sometimes I get trouble from math students because they don't like it, but if you want to have the formal definitions, I can give it to you, but maybe outside the lecture because it will confuse the majority of the students. But I will try to give you the main idea. So if you are familiar with the notion of operational semantics, then you will understand what I'm talking about. Okay. So, in fact, related to what I was saying is that if you take any rule, it's just syntax. It corresponds to infinite set of instantiations. And this is important to keep in mind because such a rule tells you that if you have any state S, and in fact, we have infinitely many states S, then you can add any new element and X is ranging over the set of integers, so there are infinitely many. You can add such an X to such an S if X is not already in S. So let's look at some instantiations of this rule. For instance, this is one instantiation of this rule. It tells you that if S is 2, 5, this set, then I can add 4 successfully to the set and obtain a new set 2, 5, 4. Because I am satisfying the guard. You see the X is not in S. The X here is not in S. So this we call a concrete instantiation of the rule. So again, if you are familiar with operational semantics, we have a set of configurations, infinite set of configurations, and this is a transition relation. And the transition relation is usually defined by taking the set of finite set of rules and applying the rules on the concrete configurations. At this level, what you need to know is that each such a rule, the add rule, the successful add rule in the case of a set, has infinitely many instantiations. This is one, this is another one. You can add 7 successfully to the set 2, 5, 4 and obtain 2, 5, 4, 7. So, and then you have infinitely many instantiations. So you can imagine that you can take any set, you can take any one of these rules, you can take any X and see either you obtain false and true. In particular, for instance, if I try to add 5 in this case, then this rule will not be applicable because I will not satisfy the guard, but this rule will be applicable because I am satisfying the guard. We will see some examples now on this. So the only thing I want you to know now, from the point of view of semantics, each rule in the abstract data type corresponds to an infinite set of concrete instantiations, each of which allows you potentially to change the state of the abstract data type by matching with one of the rules. Again, if you are familiar with formal methods, in general, you may be able to apply several rules to the same configuration. So for instance, if I have this configuration here, I can apply this rule, but I can also apply contain 5 true to the rule because this rule is satisfied. So you, in general, you get a transition system with infinitely many states and with which is, in fact, even infinitely branching, etc., etc. But I will not go through this here. So if I confused you, just I want to tell you that a role corresponds to infinite set of instantiations, and that's it. Okay, so this allows me to define a notion which I call traces. So what's a trace? A trace is that you start from the initial state and you just apply some operations that are enabled according to the rules. So this is a trace, it's an empty definition. Start from the initial state. So for the case of a set, we know what the initial state is. This is defined by the abstract data type. If you have different initial states, you start with one of them. In this case, we have only one initial state, so I start from that initial state. S init, this week I call S0, and then repeatedly apply rules, apply a sequence of rules. So I take my S0, which is S init, and then I apply some rules. Remember that each rule is an operation, where each operation is an atomic execution or method. Name applied to some input and output. So I get a new state S1. And then I apply again some other rule, op2. I get S2, etc., etc., until I get Sn minus 1, in which I apply op_n. And finally, I get a new state, final state Sn. Now, so this is the definition of a trace. Start from the initial state, which is the empty set in the case of the abstract data type set, apply a sequence of rules, and then finally collect the sequence of operations that you have generated. So this is the sequence of operations that I generated in this particular derivation, in which I started from the initial state, and which I repeatedly applied rules. And then I look at the operations that I generated, and then I obtain a trace, a question. Let me see. Rules or methods? Well, I mean, we will see soon. So in fact, it's rules, but because you have to match with a rule, and as a result, you get an operation, which is the operation that you perform when you apply the rule. Is it clear, Hassan? So, okay, good. Very good. So we'll see some examples. So what I'm doing is that I'm taking some initial state, I apply the rules one by one, or in some order, and then I collect the operations that I have generated. And then I call the result a trace. Let's look at some examples for the set. So start. So now from now on, I use this diagram quite often, which is time. I mean, time is not real time, it's logical time. It just counts the number of steps that you have performed. And this we will use to relate abstract data types with what we call histories, with sequential programs, with concurrent programs. So as I will tell you later, you will get a hierarchy of abstraction of abstractions where you decrease concreteness. So the abstract data type, the notion of an abstract data type is the most concrete level. And then when we reason about correctness of programs, we use the notion of a trace of the given abstract data type in a way that I will explain later. But now we know an abstract data type, we know its semantics in the sense that you have states, you start with the initial state, you apply rules, you get some operations, and you collect these operations and you get a trace. So let's see how we do this concretely. So I start from the empty set because this is my initial state according to the definition of my abstract data type, which I mentioned in the previous slides. So I say, okay, can I apply the operation? Can I perform the operation add to true? And this is related to the question of Hassan, in fact, which is quite well motivated. What I do is that, in fact, implicitly, I'm applying a rule. I have the state, which is the initial or the empty set, and I see, can I apply this rule? Well, in this case, this is the rule, add to true. And if the guard is satisfied, then I can certainly apply the rule and in this process obtain a new state. So in this case, you see that X is not a member of S because the X is 2. I have instantiated the X to 2, and I check whether 2 is a member of the set, which I have here. No, because the set is empty. So indeed, I can apply this rule and I observe this operation add to true. And I add 2 to the set, obtaining a new state in which I have added the 2 to the set. So this corresponds to applying the rule and obtaining the new state in which I have added the 2 to the state, to the set S. So you see, I am indeed applying a rule, but applying a rule consists of different components. First, you have to see whether you satisfy the guard. You observe the operation, which you are doing here. You check whether it's enabled, that particular rule, which gives me this operation, and I change the state accordingly. And then I record this event, which is the execution of the method, this operation. Okay, so now I have this state. So now I ask the next question, can I perform the operation add 5 true? Again, I check the rules, which one can give me this operation? The only one which can give me this operation is this one here, because this is the only one which gives me add in combination with true. And now I instantiate the input parameter to 5, and I check whether the rule is enabled, which means that whether the guard is satisfied, and this amounts to checking whether the X, which is the 5, is member of the state S, which is the 2 here. No, it's not. So this rule, this guard is satisfied. Indeed, this I can apply. I can get this operation, and I move to a new state where I have added the 5, the X, to the set S, and this is the new state here, and this is my this is the operation I performed. So now add 2 true. Is this possible? Well, so my only hope is that first rule is enabled, because this is the only one which gives me add and true. All the other guys will add me add false or some other method name. But now I have to check the guard. Is 2 a member of the set? So it should not be a member. But if I check the guard, you see that 2 is already a member of the set. So this means that this rule is not enabled. So I cannot put this operation here, because here I am trying to instantiate this rule here, and the guard does not allow me to do this. So this means that I just don't add it to the trace. I only add to the trace operations that are enabled according to some rule from the current state. But on the other hand, if I ask about add 2 false then I can instantiate this rule here, because this allows me to add unsuccessfully. I have false. And if you compare with the guard, you see that it tells you that you can indeed perform this or execute this rule if X is a member of S. Now, S does contain 2. So this means that this operation is enabled, and I add it to the trace. Now, how about remove 5 true? So which is the rule that may potentially allow me to perform this operation? It's this one here. And I have to instantiate the X to 5 and then check the guard, which tells me that here, that X is indeed a member of S. So this one, it is indeed satisfied because 5 is a member of the state here. So this means that I do this. This is indeed enabled. I change state by removing X from the set, which is what I do there. And then I add the operation to the trace that I am generating at the moment. Remove 3 true. So then we have to go to this rule here. And now we have to check the guard. Is 3 a member of the set? No, it's not. So it's not enabled, this operation. Yes, question. But how do you know in advance if 2 is present, if it is a big enough set with some empty initial state? No, you know, because you always start from the initial set, and then you have the history of the trace. So this will give the state of the set. So by looking at the set, I know whether this operation is enabled or not. Is that clear? And big enough set, I don't understand what it means. I mean, it's just a finite set. So I started from the empty set. I applied the number of operations. As a result, I am in a given concrete state, which is a set, a finite set, and I just look at the set and see whether it's enabled or not. I mean, this is an abstract mathematical object. How you do this in programming, we will come to that later, how you implement a data structure that satisfies this specification. But mathematically, I have a set concretely, because I just apply these operations, all of which are enabled by definition of a trace. And I know that if I apply them to an empty set, then in this case, for instance, if I apply these operations on this set here, then I get exactly this set, and this is well defined. Is it fine, Hassan? Hello? Maybe. Yeah, good, very good. Okay. So remove 3 false. Is this enabled? So now I have to take this rule, and if X is not a member of S, then this will be enabled. Yes, it is. So I can put this here in the trace. Contain 3 false. Is this enabled? Well, I have this rule here. I go to the set. If X is not member of the set, then it is indeed enabled, which is the case here. So I add it. So you see here, I started from the initial state, which was an empty set, and then I added operations one after one. I applied the rules in some sequence, provided that at the current state, the rule was enabled, and therefore I could add the given operation to the generated trace. So finally, add 9 true. Is this enabled? Yes, because you can do this, and 9 is not a member of the set, and you can add it. So this is one trace of a set. So what we did now is that we generated a trace, which was of this form here. And now the trace, as we said, is you just collect the operations that you have generated. It's just this one, this one, this one, this one, this one, this one, this one. So this gives me a trace. And now I define the set of traces of the abstract data type set by being all the traces that I can generate systematically applying the rules, namely starting from the initial state, which is the empty set, and then applying enabled rules to the intermediate states. And this is a trace that we generated in the previous slide. So indeed, this is by definition a member of this set. So the set of traces of an abstract data type, a set in this case, this set is defined by all the traces I can generate according to the semantics that I defined. So accordingly, this is also a trace of the abstract data type set, because I add 2 successfully, I add 5 successfully, and then I check successfully for the containment of 2 in the set, which is true. This one is not, it's not a member of the set because you cannot generate such a trace, because here you have added 2 to the set, you have added 5, and then you check whether the 2 is not in the set. So this is false. It's not a member of the set. And using a similar reasoning, this is not a trace in the set. So again, a trace of the abstract data type set are all the traces that I can generate by starting from the initial empty set and applying the rules according to the semantics. So any questions, please? Now, I just want to emphasize that all these operations that we generate are atomic. They do not take time. This is very important, as we will see later, where we have non-atomic operations. By atomic, I mean that you apply the method with the input and you get the output all in one step. In reality, when we implement programs, this will not be the case because executing an operation will take some time. So first you will call the remove operation, give it some input parameter, and after a while, the program will perform some computations, after which you get a result. So you'll be an invocation and then a response, as you will see later. But at the level of an abstract data type, we assume that all the operations are atomic. Meaning that everything, applying the rule, giving the input, getting the output, all will be done in one step, as we saw here. So because I was talking about some hierarchy of abstractions, so this is the most concrete level in which all operations are atomic. When you go to sequential programs, already there, operations will not be atomic. So this will be the next abstraction level. But if the program calls a method, say remove, then it will wait until it receives the result from the data structure before proceeding to the next operation or to the next instruction that it will execute. But in the case of concurrent programs, even that will not be true, because maybe some thread will call remove 3, and then some other thread will add 3 to the data structure while this original thread was waiting for the answer from the system, and then it will not be clear whether the answer should be false or true. Anyway, this we will take later. So now we are at the simplest, basic, concrete level where we have our abstract data types. These are abstract machines that you can use to generate traces in which each element is an atomic operation. Now let's go to queues, for instance. Let me see whether I have time. I think I will wait for some questions, rather, if there are any. If not, I think I will just stop here and then I will continue on Monday. So on Monday, I will start defining queues as abstract data types, and then I will define, let me see, stacks. And then I define what I call sequential programs, sequential histories, and then how to implement these things like that. And then this will be a program that will generate some history that you have to show corresponds to a trace of the corresponding abstract data type. So this will be the story of the lecture on Monday. In fact, I'm getting a bit more slowly than usual. I assume that I'm just trying to make sure that everybody understands, because it's very hard when you don't see the people in the room. So I am slightly behind schedule, which might mean that we will postpone the lab next week, but the lectures will follow as usual. But this I come back to later. And this is why I didn't want to announce all the assignments. Anyway, I can upload the assignments, and then for the deadline, we can wait until it's more clear where we are in the lectures. Okay, any questions? So otherwise, see you next week. And thank you very much for attending the lecture. I think it's good to attend the lectures, even if it's uploaded on YouTube. My personal feeling where I attend seminars, I pay more attention where I am, when the seminar is live. And also you'll have the opportunity to ask questions directly. But nevertheless, as I told you in the previous lecture, you are very welcome to send mail if you have any questions about the lecture. Thank you very much, and see you. Bye. Let me see whether there are. Thank you.